for the yeah, thanks for the handoff, James.
All right, I'm going to go ahead.
Go ahead.
You go ahead.
Okay, I just wanted to start off by thanking everyone for being here at these odd hours and odd places. This is definitely the type of event that I would have traveled for and really enjoyed the conversation. So I'll be watching the chat. And well, let's see how this works. So I'm going to start tonight with an introduction to Greenhill software and functional safety. Functional safety is one of those things that it sounds like it's something you ought to know what it is, but then when you dig into it, you don't. So it's sort of a cryptic topic for a lot of folk. I'll talk about why you might want to use Rust in a functional safety system and explore whether it's suitable for functional safety systems today. So here's an overview of Greenhill software. We're the largest independent provider of software for embedded systems. We've been in the industry for 35 years. We started out as a compiler company. In the late 20th century, we added an integrated development environment and then a real-time operating system to our offering. And today we're the leader in safety qualified tool chains with our multi-IDE and Greenhill's compiler, and safety certified operating systems with our Integrity real-time operating system. I've got these posters. We use these at trade shows. We have them around the office, and they highlight different customers. And this grouping here shows our traditional market of safety systems, planes, trains, and automobiles. If you drive a Japanese, US, or European produced automobile, then you likely have some Greenhill software in there because we've been shipped in 130 million vehicles to date. In aviation, if you went back when we used to fly on commercial aircraft, you probably flew on an aircraft that used Greenhill software. All modern fighters in the West use Integrity for their operating environment. And a lot of transportation infrastructure, trains, is built around our Integrity RTOS. But safety markets are much broader, really. They also include things like agricultural equipment. These have whirling blades of death, and when you want the whirling things to not be whirling so it's safe, then you want assurance that it's going to be safe when, especially when the operator is out around the equipment. So there's safety certification standards for agricultural equipment. Medical's interesting because it not only has safety, but also cybersecurity standards these days. And that's a new requirement. And then there are kind of niche markets. NASA and JPL use us in spaceflight equipment, as well as in defense. And then, that's an HP printer. The cost of a failure in a consumer appliance isn't a safety issue, but it's a big business issue. So reliability matters there too. So what is functional safety certification, and what role does it play in these products? Well, functional safety certification provides assurance that a system was built taking the safety of the system into account. Now, notice that wording. It doesn't assure that the system is safe. Only the processes that are essential to building a safe system are followed. See, it's a little cryptic. It's assurance that you followed a safe process, because that's something that you can measure. Examples of functional safety standards include the US FAA DO178C for software used in commercial aviation, ISO 26262 for automobiles and software in automotive electrical systems, and IEC 61508 for industrial automation, factory floor equipment. Now, the interesting thing is, even though we've got these different standards from different fields, They're all pretty much the same, only a little bit different. They all talk about goals, supporting processes, and work products. And this is really the secret decoder ring. If you ever go to read a standard like 26262, and you're wondering, well, what do I have to do so that my product is certified? What you're looking for are the processes. So the processes are things you do to achieve goals. And work products are what you show an assessor to prove that you followed the process. It sounds simple. It is, but it's a lot of work and there's a lot of details. The good news is that the processes and work products are typically tailored to the risk level. For example, using different types of structured methods for risk analysis based on risk impact. If the product is low risk, you don't have to look too hard. All of these standards have different levels of assurance, where the highest level is for life-critical systems, and the lowest level are for systems that have much less impact. For example, an instrument cluster in an automobile, a safe state for a graphical instrument cluster is actually blank. The safety rules there say it's better to show no information to the driver than to show incorrect information to the driver. Now that is considered a middle-low safety level. Now compare that with an ECU controlling a hydraulic system on a commercial aircraft. If that fails, it could be catastrophic. So that requires a higher level of assurance, and therefore more work, more processes, more work products to achieve the higher goals. So that's what functional safety certification is really all about. So typical development of safety systems follows a V model of development. Down the left side, you do the design work to avoid systematic faults. That is faults that are due to failures in your systems, failure in your processes to engineer a correct system. You should be able to anticipate these and mitigate those risks. Now, on the upper side, heading up the other side of our V model, we're going to contain the faults that are unavoidable. You know, if the chip fails, the chip fails. What is it that you do about it? What is the system supposed to do when the chip fails? So that's what you provide assurance for on the upward side of the V model. And at each level of abstraction, you pair a design process with an assurance process. So you assure your detailed design through unit testing. You assure your high-level design through integration testing, and requirements coverage through system testing. So this is the typical flow of development in a safety system. Here's why we are interested in Rust. We have a theory. We have a theory that using Rust reduces systematic faults due to memory-related bugs. Remember that 70% of bugs that James talked about in the keynote? So we see the Rust borrow checker enforcing correct by construction pointer use and memory allocation. This is a big deal because that's where the bugs are. And not only is that where they are, they're there because they're very difficult to test for, because they're very state dependent. We also think async await is a big win for RTOS application code readability and therefore reliability. You know, today for event-driven code, we often are writing state machines with big switch statements. And async await unwraps that state machine and makes it read like procedural code. And humans are much better at procedural code than declarative code. That's why we're not all programming in reactive functional programming languages, at least not commercially. And then we think that the benefits of Rust actually extend above the unit level. Correct composition is also enabled by the borrow checker. So we think it reaches further up. But there's a context here. That context is this V model, and it's been developed over a very long time. Functional safety isn't a new concept. The V model, preventing systematic faults, it's not a new thing. So, when we bring in Rust has its C foreign function interface. And we think that's how Rust has to be integrated into safety systems for the foreseeable future. You've got Rust. Maybe you have other compiled code from other authoring systems like UML or other model-driven tools like from system design companies like MathWorks. But in the end, it's a C world. All of the processes that get you to implementation and then back up are geared around a C-compatible ABI. Now, the world of embedded systems is a bit different than general purpose operating systems. And this importance of a C tool chain really goes very deep into what is different about embedded systems. The big thing is embedded systems are diverse. There's diversity in the type of cores that are used. ARM is, of course, very, 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 very popular and embedded these days. Intel's there also. There's a lot of vehicles driving around with ARM and Intel chips, especially in the instrument clusters. You might be surprised to know, though, that there's a lot of life left in PowerPC. PowerPC is we're still seeing new starts in automotive and also in aviation, both commercial and defense. These chips are really well known. They're worst case performance. And there's a lot of code. Code lasts forever. Code lasts a long time. So when you have an operating system that you've been flying for a long time, you don't want to change it because that's risk. People stick with PowerPC because to them it's a risk to move. Now, a newcomer's RISC-V. We're seeing some applications that are on PowerPC move to RISC-V instead of ARM for future-proofing. It's seen as having a longer tail, more vendors, avoid vendor lock-in. And then there's kind of some funny processors that you mostly only see in automotive, like the Infineon Tricore and the Renesas RH850. So why do you care that there's all these different cores? Well, it's because they all come with different tool chains. At Green Hills, our tool chain supports all of these processors. And that's nice for the customer because the compiler flags, the linker, everything is all the same. But ARM has an ARM compiler. They want their customers to get the most out of their processor core, so they provide their own compiler. Intel does the same. Then there are independent vendors like IAR. And then we have our open source alternatives, GCC, Clang. So, there's diversity here. And where it really hits home is in the linker. Linkers are actually pretty magical things. They perform magic in embedded systems. In a general purpose OS, you almost never interact with the linker. Maybe you need to set an LD library path or make sure a DLL got into the registry or something. But in embedded systems, they are touching your code in a very first-class way. For example, linkers will modify your code to reduce size, things like varchol patching, common sub-expression refactoring in the binary code to reduce code size. And then we've got overlays that'll take parts of your code, chop it up, put it into separate binaries. So, these are pretty deep features. Now, they'll also modify your code for functionality. And this typically happens with silicon errata workarounds, where you throw a magic flag and all of a sudden a no-op is inserted in between two instructions where it hadn't been when it came out of the compiler. This is a real safe way to patch errata that are exercised by certain instruction sequences, because it doesn't matter where the binary came from as long as it's linked by this linker. And linkers also feed downstream tools. They tell the bootloader what's live, what's not, what needs to be cleared, and where to load things. So linkers are first-class objects in an embedded chain, an embedded tool chain, whereas you just don't see them much in the general purpose world. Now, these magical features, they're often implemented as bespoke features. So this entrenched C-based ecosystem really goes all the way down to the linker. And if you're going to bring a new language in, it has to support the diversity of cores and the diversity of linkers, diversity of tool chains throughout the ecosystem. An entire Rust build is a ways off because of how long code lives, and not just the code, but the supporting processes and infrastructure around your application. Take a look at build tools. We have a builder. We like it. I like it. A lot of our customers use makefiles. They use CMake, or cons, or bitbake, or cargo.toml. There's a gajillion build tools. And if you want to fit in, you got to fit in with the build tools and the operating systems and the test tools. Bespoke test runners. That's what you find in embedded systems. I didn't have time to get a picture of the test lab at Green Hills. Our test labs, we have a board for every BSP that we support. And connected to it is a JTAG probe, a serial port, a network power supply, and an Ethernet port. And we have hundreds of these. And we're running validations constantly. And you can't do that with an off-the-shelf system. You have to tailor it to your needs. And that's what our customers do as well. And there are other essential tools in the build chain that are used to this C-based flow. Things like license scanners that read your code and look for whether your engineers accidentally cut and pasted from open source, and look for open source license headers. And then things like secure boot signers. So if Rust is to be adopted, it can't be tied to a single tool chain and embedded. And this is really what's different about embedded and therefore functional safety. So where are we today? So if you go look at the Rust embedded book, you'll see a system that kind of looks like this. It takes Rust and a cargo.toml as input, and It'll connect to a Cortex M3 based system. It's soup to nuts. This is a really good system. If you haven't done embedded systems programming before and are curious, this is a great system. There's a talk later on in the conference about, is Rust embedded the new Arduino? Well, take a look at this board over here. This board's literally sitting on my desk. This is an ST Nucleo board. They provide Arduino images for this board. The daughter card, that's an Arduino compatible NXP sensor module. I bought it for a Geek Time project that I'm doing. The Cortex M3 based software hardware abstraction layer that Rust Embedded provides. The RTFM real-time for the masses. This is a great system for building small embedded systems. And it just works. And that's really one of the things I like about it. And that's why I really do believe, yeah, this is a better way to go than an Arduino. So let's just look one level deep here. What's different about programming Rust Embedded than any other Rust platform? Well, one thing is this link map, this link.x file. This is input to the linker. Remember I was talking about linkers. So in embedded systems, you have to tell the linker where to put things because you've got a lot of different types of memory in embedded systems that you don't have in a general purpose OS. In a general purpose OS, everything's just memory. It's just RAM and pages. It looks infinite to you. Well, memory is not that like that in embedded systems. You have flash. Typically, you're booting from flash. Rust Embedded will flash it for you. It's really awesome. Then you got to manage your RAM. And sometimes you'll have different types of RAM, fast RAM, external slow RAM. So that linker command file is really important. So that's a difference here. And then you've got the cargo run command that doesn't just shell out. It actually talks to this part of the board here is what's called, this is a small JTAG run control thing. They call it ST-Link. And cargo run for cargo embedded actually talks to this thing and resets the whole board and flashes memory images through this and provides your debug interface. So really it's providing a link map and cargo run. Okay, and that's what's different here. Oh, and a bunch of really awesome crates. So what if I wanted to use this system with something other than this Arduino-looking board? What if I wanted to use it with something more industrial strength? What do I have to do? Can I take Rust Embedded as it exists today and use it in a more commercial manner? So this board I'm showing now, this one's on my desk as well, actually on a little rack next to my desk. And, some things to note as compared to the Hobbyist Nucleo Arduino-based board. This one's got a display. Okay, it costs a little bit of money. It's got Canon RS-232 down here. But really importantly, it's got an ARM CS20 trace connector, and I've got it connected to a Green Hills trace pod. If you've not ever used trace debugging, oh man, it can be so useful, especially in embedded systems where, because you don't have memory protection often, when bad things happen, really bad things happen, and you'll end up in an error handler, and you'll often wonder, well, how did I get here? This trace pod, connected to the trace port with the appropriate electrical on this higher cost board, lets me do that. So the extra peripherals, the extra debug, that's what makes this a more commercial-oriented board. This is, in fact, a reference board that's frequently used for medical designs, infusion pumps, and those types of systems. So I asked the question, what do I have to change if I want to use this board? Well, the first thing is, I already have this board up and running with the Green Hills toolchain. I've got a Green Hills linker command file. Oh, shoot, but I'm using the Rust linker here. Okay, what am I going to do about that? And then Cargo Run. Cargo Run knows how to talk to OpenOCD devices and run control them. The Green Hills Probe is not an OpenOCD device, so I can't just immediately use Cargo Embedded as it's shipped. But I don't have to go very far. And that's because Cargo will also build a Staticlib. It'll build a crate as a static library, a .a file, fully linked with everything but the operating system. This .a file looks to a tool chain like any other .a file. So all those integration points are now super easy, because now I can use my GHS linker command file and C code that compiles with the Green Hills compiler and even an RTOS, because I can pull that static library into my Green Hills builder. This is our project manager. So with that static library and just changing my crate to be a static lib instead of an executable, now I get into the Green Hills toolchain. And now I can run with Green Hills Multi, and now I can do trace-based debug on this commercial board. So, you know, the Staticlib integration, it means we don't need to modify Cargo to know about a different linker. We could modify Cargo to know about a different linker. We could modify Cargo to know how to talk to the multi-debugger, but we don't have to do that. And we don't have to modify Cargo to run test tools, secure boot encryptors, license scanners. This is a really good integration point, and it's supported today. Now, there are downsides. We lose Cargo Run. I put that with strike through because I'm not sure, in an embedded world, I'm not sure Cargo Run's a great thing. For the use model of an Arduino, yeah. In a commercial world, eh. But Cargo Test is a loss. You know, having an ubiquitous test runner and really well-supporting test-driven development, that's a really good thing. But, you know, Cargo Test today isn't exactly embedded friendly. So I wanted to use this opportunity to invite the community to consider how Cargo Test can be targeted to embedded. You know, like right now, Cargo Test without changes or, you know, pulling in things requires a test runner. You need to be able to run, and it requires a lot of integration if you're going to pull it into a test environment like we have at Green Hills and our customers have. But what if it just output a static lib? Then we could integrate it. But then we get into things like the size of the binary. I don't know if features are enough to where you could just keep rebuilding and get static libs for each of your tests to make sure that they fit in the amount of RAM. I love Cargo Test when I'm running on a general purpose OS. I'd love for it to be more embedded friendly. Okay, so, you know, for general purpose embedded non-safety critical development, I've been able to use Rust embedded, and I really like it. I like it. So what's really missing for safety, using it in a safety system? Well, safety qualified tool chains is a gap. And if you saw James's keynote leading into this, then you know a bit about sealed Rust. And we like sealed Rust. We endorse sealed Rust. You know, you really need a language standard that's on the sophistication of ISO-C to support qualification requirements. Now, if you look at the backing material behind sealed rust, you'll see that James calls out, and Ferrous Systems calls out, and the supporters of sealed rust call out that rust is already in a really good place. Because of the test infrastructure and the RFC process, the rationale for the design choices is there. This is a good place to start from. But the level of rigor needs to be brought up, the level of formality and stability. I've said a couple times that code lives forever. Code lives much longer than you ever possibly imagine. Protocol stacks are really an example. Some of the CAN stacks in automobiles from the big companies, 15, 20 years old, same software, they just keep rebuilding it. It's too expensive to test again. So the stability in the language that sealed rust takes beyond the quarterly releases, that provides a level of certainty that the long-lived code and safety systems needs, in addition to the formality of the language so that accurate testing and test coverage can be achieved. So that's a piece that's missing for safety. There's some smaller things too in the C foreign function interface, a couple niggling details like C volatiles and C bit fields. It's a C world today, and it will be for the foreseeable future. And I know there's spirited discussion about volatiles and bit fields, but I think these need to be not just crates, but either standard crates or more than just a pointer type. I think there's more to do here. And then another aspect of the C foreign function interface is BindGen as it exists. BindGen, open source BindGen, I think aspires to the wonderful ideal of, wouldn't it be great if you could just call C from Rust and just hit a button? It's not that simple. BindGen's built with Clang's front end. And if you have a different set of headers, well, it's not quite going to work. Or if Clang is a little bit different than the C compiler that the code you're trying to translate uses, and as advanced as our standards are these days, there's still always little differences in C compilers. So, BindGen just is portable, and it has some attitude about volatiles and bit fields. I don't know. It's not complete, and I don't know if it ever will be, and it probably doesn't even need to be. But a conclusion I've come to is that each tool chain will need its own BindGen to really help ramp up the productivity. Today, oh boy. Well, that's a nice internet glitch. So in summary, Rust today is ready for use in non-safety critical embedded systems. We think that Staticlib is the best integration point today. There's still some work to do at the C foreign function interface level, but this is a usable system for building non-safety critical embedded systems. To take it over the finish line and really get the advantage of the language that we all see, we think that sealed Rust or something like it is needed to enable use in safety systems. And that's what will unlock commercially available qualified tool chains. I don't think any one vendor or any one program adopting Rust is going to be able to pay for all the process that provides the assurance that we've built a system that properly takes the safety into account. So that's the end of my talk. James, do you want to help me moderate questions, or how should we take questions? think you're muted, James.
I am muted. Thank you. Yeah, so we've had a couple questions in the chat. So we're a little over time, but we've got time for a couple questions before we go back into break. So the first question was from Evan Richter. And Evan Richter asked, Jack, I would love to hear your thoughts on efforts to help the difficulty of testing on embedded platforms. Fuzzing and coverage guiding fuzzing in particular has really taken off in the last 5 years, but still it is very difficult to harness embedded solutions into a fuzzing target. Any thoughts on fuzzing or other dynamic analysis techniques?
Yeah, one of the difficulties of embedded systems is the lack of resource. And so that's one problem with test generation techniques like fuzzing. We do fuzzing at the API level. So it's certainly a great way to check for robustness. In general, we found the usability of test generation tools to be lacking. And I'm not sure how to resolve that. We use various test generation tools, both in-house tools and third-party tools for test generation. They're all really awkward to use. And I think that the only way they get better is more people using them and not being willing to put up with low quality. I think EDA tools fall into this trap as well. The quality of electronic design automation tools, things you would use to program FPGAs, is incredibly low. And the cost is incredibly high, but the number of seats worldwide is low. So my hope is that as more people are involved in safety critical systems, and the mandate for using safety critical systems and functional safety certifications is growing. Just look at the European car safety standards. I think that's really the key to making these tools more usable, is more people demanding better tools. And where necessary, just writing them in open source.
All right, I've got a second and probably last question for you. B. Brown in the chat is asking, I appreciated the Staticlib example of how to plug into an existing project, but do tool companies worry that their long-term market share may reduce if new projects pick a fully open source tool chain? With C and C++, the open source tools can be so clunky that IDEs like IAR add a ton of value, but the Rust tool chain is just so easy and user-friendly, I'm not sure if I need an IAR, although I may want the compiler backend still.
My attitude about open source is if open source is good enough for you, go for it. Our customers find that open source doesn't have properties that they need for long-term support and functional safety. They don't have certifications. They don't have long-term support. They may lack features for embedded systems. Companies often pay us to customize tool chains to exactly their specifications. So when open source is good enough, hey, that's great. I'm not threatened by an open source Rust. There's a reason that closed source exists, and there will continue to be the need. Look at debuggers. I think there's a reason that people on Linux don't use debuggers, and it's because GDB is not a good debugger. It lies to you constantly about your data values and how you got there and where you are. A trace-based debugger like ours or from one of our competitors like Lauterbach, oh my goodness, it just lights up the world. And the information that we can show you about your system by coupling our compiler and our debugger and our linker and give you unprecedented visibility into the timing and behavior of your system, that's just not stuff that open source is good at. So open source is good at stuff that's used by a whole ton of people and less good at stuff that's used by fewer numbers of people. And, we're always going to have value is what I think. Greenhill, there will always be a need for a company like Greenhills, even as open source takes more and more of the software content, as you've observed.
All right. Thank you so much, Jack. I know we'll probably have at least one more question in the chat, and it'd be great to if you could comment on that on the Matrix chat. But I know you also need to get to sleep before you come back for our safety critical panel tomorrow for you and later today for us. So thank you so much for your talk. And we're going to go to break now, and we'll be back in a couple minutes with our next talk. Thank you, everyone.